data and how to transform complex networks. And according to Sarah Hoffman's talk from Friday, it's going to get even more complex, how we can make it more simple and usable for a specific use case. So,
thank you, Yair. And so today, my topic is highly relevant for those of you that working with the OSM data road network, and even more relevant for those of you that trying to do active transportation analysis. So the first question would be, what is actually active transportation? So before diving, let's just explain what is active transportation, which is actually any movement of people or goods that originated from the human energy, such as walking, bicycling, and so on. The active transportation has a lot of benefits from different perspectives. For example, reduce obesity if you talk about health benefit, environmental sustainability could be reduce air pollution, congestion, crashes, and so on. And when you talk about the community well-being, so it's just like foster social interaction, it could be reduce stress, and so on. So what is the motivation for this work, for this project? So 2 years ago, when I still located in resided in Santa Barbara, so I partnered with 2 colleagues, one from Israel and one from Turin, Italy, and we tried to suggest some kind of street profile. So every street will be classified into one of the profiles based on the attribute regarding to the proximity, to the accessibility, like proximity to amenities, transportation, and so on, and as well as physical attributes like sidewalk width, slope, the noise, the noises from the cars, and so on. But in order to implement this idea, so we have to use well-defined network, which means that every street represented by one center line. So for Tel Aviv, it was very easy to do that because we have, actually everyone has access to the GIS city website. So we can just download the network and we have very good network. But it wasn't the case for Torino. So our default option is go to OpenStreetMap, which is great. But for our case, it's too detailed. And you can see that's the right side, so you can see the network we got. Just to explain the problem even more deeply, so let's take this street as an example. So in the reality, street usually has more than one lane. There are at least 4 lanes, 2 for cars and 2 for pedestrian. It even could be even more detailed. And in OpenStreetMap, we try to digitize the reality as much as we could. So this street on OpenStreetMap is presented by 4 lanes. But which one we need to choose in order to create center line? And that's the question we tried to answer in that project. So there are main 4 components for this algorithm to solve or to address this problem. The first is some preliminary task, and then we need to identify the multi-lane or the parallel streets, the parallel polyline street when we detect them. So now we can start with the simplification. And finally, our network has been affected by the component number 3, so we need to fix this topology error that happened because of component number 3. So let's start and dive into each component. So the preliminary tasks include obtaining the data from OpenStreetMap by using OSMNX a Python library that's created by, or developed by Jeff Boeing, which is great library, not only to download the data, but also to do some, I mean, he also automatically fix all the error that's occur in the OpenStreetMap data because of people sometimes map polyline differently on OpenStreetMap. And then we need some kind of filtering or some kind of remove unnecessary polyline. For example, we don't need streets that are not relevant for active transportation analysis. For example, highway, we don't need roundabout as polyline. We need them as points. So we'll add them later as points, as I will explain later. And finally, we are working only with polyline with name. Polyline without names are removed because we assume that polyline without name are not part of the final street layout. After that, we can move on to the identify multi-lane street. So we assume that multi-lane street or parallel polyline has happened if the group of polylines have the same name, roughly have the same angle, roughly, it's very important to highlight it, and are in close proximity to each other. So the first bullet is quite simple, it's quite straightforward. Give me all the polyline with the same name and group them into one group. For the second one, we reclassify the polyline in the same group using dbScan. Now, dbScan not using dbScan based on the value of the angle. So dbScan not only reclassify the data, but can also find outliers. The outliers will be excluded for the next stage because we already know in that point that they are not part of the multi-lane scenario. And now we have, for example, in this, for this polyline, we have 3 classes. And now for each classes, we can move to the next condition. So we create, so let's say we have a bunch of polyline with the same name and roughly the same angle. So for this group, we create buffer around each polyline and move and shift it to the right and to the left. And if this shifted buffer are intersect with another polyline within the same group, that means we have multi-lane or multi-lane scenario or parallel polyline, and those polylines should be reshaped or simplified into center line, and that's take us to the step number 3 or the component number 3. So I'm not going into much detail about it. I just say that now we have a group of polyline that we know should be simplified. So the main idea around it is to find 2 points that are represent the new center line the best by using the function here, the equation below, by looking on the distance and the angle, and that's form the basic form of the new center line. Right now it's like a segment, like a straight line, only 2 points, the beginning and the start, the beginning and the end, or the start and the end. But we assume that the center line could be, the direction could be changed over the way. So in order to do that, we need to add more points, and now we implement that. So the idea is to break the center line, the new center line, into a small segment, and every x meters, we find the closest polyline from the original group of polyline, and see if the distance between the new center line and the closest polyline is smaller than a threshold. If it's larger than this threshold, that means that the point, the closest point from the closest polyline to the center line should be added to the center line. So instead of one segment of new center line, now we have maybe only those two, but maybe we have a lot more points that can be added to the polyline. So instead of like one center line, one straight line, we have more points that can help us to change the direction of the line and maintain the original shape of the bunch of those polylines. But because of number 3 components, so we still now have some topology errors. So because it's very technical and use existing algorithms, methods, so I'm not going to explain how exactly that I did it. Anyway, so just connect just connected the polyline, and then we also need to add the roundabout that we remove in the first step into our network. So the idea is to take all the polyline that create roundabout, shape it into points, and then all the center line with dead end close to the roundabout as a point, as was connected to the roundabout. And we had another case when the polyline, when we have straight polyline very close to the roundabout. So in this case, we also add this roundabout into the polyline. And that's the end of the methodology. There are the main things around the methodology. And let's go now to the result. So our results are focused, of course, on Torino in Italy. And here we can see the first road network without any processing, just using the OSM Next to download it into the local computer. After the pre-processing, we got the purple network, which is already, we can see it's different from the green one, because actually we remove all the polyline without names. So remove a lot of polylines. We have the numbers on the left. After the simplification, we got this network. From this zoom, we can't see anything. So let's go. Let's zoom into one of the parts in Turin. So it works. I mean, instead of like 3 or 4 polylines, now we have 1 polyline. But as I said, the topology has been affected by this process. For example, here, the roundabout, and so on. So the last or the 4th component, fix it, and here you can see the same network fixed and ready to analysis for active transportation. Now I want with you to go to different layout configuration from the very simple to more complex one, and see where the algorithm works well and where more work should be done. And let's start from the simple one. So figure 8 is like very simple configuration. So actually we expect for nothing. I mean, everything should be as the original network. Is that exactly what happened? So we are happy with that. In figure B, all the red was removed again because of the name. There is no names for this polyline, so they were removed. And then we have C, which show us that even if the polylines are close to each other, they have quite the same angle. As long as their name is different, they are not going to combine into one center line, which is, again, it's good for active transportation analysis. The next level is more complex layout. And usually it works again, but we already can see two places where the algorithm failed. For example, in this curve, so instead of one center line, we still have two polylines. In figure F, we can see this intersection. We expect for one center line, but we have two center line. That's very easy to explain why it's happened, because we are based on the angles. But in this case, actually the angles are the opposite. So for the algorithm, it does not aggregate polyline like this one. And even more intricate layout. So again, mostly it works well, but still we have some things to improve. What's happening here, for example, this is area, because this area, there is names for these those polyline and so on. So we also made some validation, which means we choose 10% of the street and inspect them manually. We did it in Turin, Italy, as I showed you before, and San Francisco and Tel Aviv, Israel. For San Francisco and Tel Aviv, 90% of the street was good connected, was as we expected, was aggregated as we expected, and the rest was between like minor changes that should be done to more bigger failure. Let's call it that way. In Turin, I think because Turin consider more complex layout, so the rate success is about 80%. Now we are in Nairobi, so I've tried the algorithm on Nairobi, and this is the data before any processing, and then after our thought network, and we can see just from this zoom the problem in our algorithm, at least here in Nairobi, I guess in other countries and cities, because if you remember, we remove all the streets without names, because I assume that street without name means they are not important to the final result. But in some places, there is no name, or people didn't add this information to OpenStreetMap. So all these areas are excluded for next analysis for area here. Maybe here it's like walk. Maybe this one is it's okay. But I'm sure people live in this area and that area. So that means that, that's actually lead me to my next goal for this algorithm. So what to do with polyline without name? There are two possible options. The easy one is just say, okay, if you are without name, just add you to the final result without do any simplification. The second and more complex one is to on the top of the current algorithm, try to add more analysis, more assumptions regarding only to the street without name. For example, if this street, looking on the tag highway and decide if we continue to try to simplify this street or not, or look on the distance and the angle again, but only on the street without name. The second thing I want to do, because the topology, the fixing the topology works quite well, but we still some things to improve. And one of them is actually because we know at the beginning which street connect with which street, so we can use this information, and at the end of step 3, make sure that the street that was connected at the beginning will be connected at the end. And finally, the performance right now on my laptop is about 20-30 minutes to run the algorithm from the end to end. So it's on the entire city, like Tel Aviv, like San Francisco, and so on. But I think we can improve this as well. And finally, the algorithm has already been used for the project I just told you that about street profiles, and also it's already been used and going to publish very soon, like improving the dominator ranking for bicycle and pedestrian safety in different cities in California, and assess bike network connectivity and safety in 2 mid-sized California cities. And thank you for your time.
Thank you, Chituv. So questions from the audience?
So I'm fascinated by the algorithm here. That's very interesting. Seems like you've made a lot of progress. But I don't quite understand why this algorithm was necessary to begin with. When we at ITDP use OSM data for active transportation, especially for walking and cycling, we want a network that's as detailed as possible. We want to understand all the little cross streets and the alleyways and the pedestrian bridges and the crosswalks and all that. It seems like what you've done here is very much factor that out. And I've even talked about some examples, but I think you understand my point. So I'm curious, what does this get you? What is the ultimate goal?
Okay.
Just the question was about the motivation, because in some applications, or maybe many applications, the complexity or the richness of the network is something that is required.
So thank you for your question. And the answer that actually we need 2 networks. We need one network which include all the data we need, but eventually we need to take all of this data and aggregate into, let's say, we have information about bus stop, things like that. Okay, so we are working with the basic on the detailed network. Take all of the data we need, and then we need to apply it on a well-defined network, which we have only the center line. It doesn't mean like we throw away the OpenStreetMap network data. We still need it, of course, and I mean, I don't want people like start to think we need to change direction and make the OpenStreetMap data simple. No, this is not my meaning. Beside OpenStreetMap data, we still, in some cases, at least in the cases I have approached, so we need this simple network. So it helps us to take all of this information and put it into a simpler OSM road network or centerline road network.
One of those cases where you need the simpler network?
Yeah, for example, for me to build street profiles, okay? So I need to build first. I need to build road street networks, okay? But on OpenStreetMap, what is from all of the lanes I have, which one I could choose? So, here we try to calculate the length in the second application. We try to calculate the length for each street. Which one of the lanes I will choose between to calculate this. So the center line will actually help me to do that. But again, the main point is I still need the detailed OpenStreetMap network. At the end of the process, you can take the information and put it into more simple, like the center line that represent the street.
So we have one on valueless. This is not only an issue for analysis, but also map styles could be improved with simplified street network on lower zoom levels. Do you see a way to implement that?
I think to understand, I mean, because it's not part of my work, so, I mean, I guess it could be done, but I need to understand more deeply the needs for this kind of mapping, so then I can adjust the algorithm to more specific needs.
I have a question. As far as I understand, you try to find multiple lanes by searching the neighborhood in the geographically space. But why don't you use the connection, the graph, to simplify? Because the lane should connect to the same crossings or roundabouts, right? You do differentiation on the locations itself. And then you see you could cluster by name and then by near location. But why not use the graph itself to do the simplification?
Okay. So the question is the identification of multi-lanes or multi-lines that relate to the same street or is based on geometry and so on, but maybe the road network, like the road graph, could be used instead.
So the graph I'm based on is the graph that OSMNX brings. But let's think about two nodes in the graph. Two nodes in the graph are not connected by one line, by one edge. No, even more. Because again, OSMNX look only on the geometry to create the graph. So it wouldn't delete polyline that connect to 2 points. In addition, think about So let's say we have 1 point in here and 1 point in here, and very close to this point we have another point in here. But actually, they present the same street but different lane, and it will be also implemented in the graph, but it couldn't help us to create the center line. I hope you can understand. If no, I can show you there on a page of sheet of paper. It would be much easier to understand, I think.
Okay, so thank you very much, Achituv. And yeah.